Okay, hello everyone. Um, Welcome back to the Python Decal. I'll be teaching today. I haven't taught all semester really, so happy to be back. We're basically now into like the meat and the potatoes of the Python Decal. We're really starting to get into the packages that allow you to do a lot of data analysis and processing, and it'll be really helpful for your final projects. So up until this point, if you've been to any office hours and someone's told you like, oh, we haven't learned that yet, or you're like, I don't know how to process this data, or how do I deal with this type of file? Well, this is what we're going to be doing basically for the next 2 weeks. Basically, all of today could be considered a final project. We're going to be doing something called curve fitting. So we're going to take a bunch of data and we're going to put a line on it. It's a very popular type of final project. So if that's applicable to you, then this is basically the lecture for you. Next week, we're going to be doing my favorite package. It's called AstroPy, and it's specifically a bunch of functions just for astronomy, and it's really fun. So highly recommend. But yeah, your proposal is due on Wednesday. That is a hard deadline. It's the only hard deadline in the class, but that's just because the instructors need to grade all of them and get them back to you, and we're trying to get them back within a week. We'll see how that goes. So if you turn it in late, you might not get feedback. So just keep that in mind. Hard deadline if you want feedback. Yeah, okay, so let's get started with today. We're doing Scipy. Hopefully, did everyone download the data? Thumbs up. Okay, if not, it's under the lectures and demos, and it's called like XY data. Very clever name. But yeah, so go ahead and download that. Okay, so yep, I'm recording. Cool. All right. So homework 8 is due on Wednesday. Homework 9 was released today, and then as I said, proposals are due on Wednesday. Okay. So to be fair, I haven't been here most of the semester, so I don't know how the other instructors have been running warm-ups, but this is how I'm going to run it. So on a piece of paper, I know that's like so old school because we're all on computers now, but please lower your laptops, pull out a piece of paper, write down your answers, and then I'll have you turn to your partner and chat about it, and then I'll ask some people to respond. So yeah, just take a few minutes, and then we'll come back together.
But that's the, I thought that was the kingdom. Oh. It's just like holes. Different, yeah, if you say that's the. Dawn. I believe it's different than actually stuff.
Okay, please turn to the person next to you if you haven't already and talk about your answers, and then we will come back together.
Pretty much.
Okay, so let's get started. All right, so who can answer my first question? What's the difference between a pandas series and a data frame? Yeah,
That series is one dimension, so it's essentially more of this, and data frame is most dimensions.
great. Yeah, perfect. I'm not going to write that out, but we'll just say series equals 1D, and then we'll say a data frame equals like a table. We could also call this like a column. That's how I think of it, but whatever works best for your brain. So that's what I would say. Great. Okay. Next question is, how do you change the name of a column in a data frame? Is that a hand? Yeah.
You would write the name of the data frame, and then in square brackets you would identify the column for which you want to change the name, and then you would set it equal to a different string value.
Great. Okay, so if I have a column, if I have a column called, let's say, words, and I wanted to rename it, how would I do that exactly? Just like what'd you say?
Just like a it would be like a different string, right?
Yeah, so we'd put it inside brackets, and then inside those brackets, I'd call it like, I don't know, sentences or whatever. But yeah, great, perfect. Okay, so that's number 2. Okay, let's do the third one. How do you get the shape of your data frame? And what's a shape? Yep, perfect. Yep, exactly. And can someone tell me what shape means? Like, why would we want to know the shape of our data frame?
It's the dimension, so.
Perfect. Yeah, it's the dimensions. It gives you the rows times the columns. Great. Very, very helpful when you're getting a new set of data and you're trying to figure out how big it is. The first thing I normally call is df.shape. Great. Okay. Next question. How do I import a CSV file with pandas? That's too big. Yeah. Great. Yep. And then I would just put whatever the name is, so name.csv. And then if I wanted to make it a data frame, I would set it equal to the variable. you can call this guy whatever you want, df. It's just standard to call it a data frame. But as you go along manipulating your data, you might find yourself like editing it and changing it. So you can come up with different names, but that's the generic. So great. Okay. And then last question. This one was kind of mean because you didn't really have the internet, but someone just name a pandas function you learned last class or one you found. Yeah.
I learned cut on the homework.
Cool. What does that do?
Just takes like a bin of input, so instead of having each value in a range, individual value, we'll put it in a bin based on a rounding of your points.
Great.
You could put in like inscript groups.
Cool. Something along those lines. Perfect. Okay, so that is the warm-up. Of course, all these answers will be posted later in the slides. You're welcome to take a look, but we're going to get going for today. So I'm going to ask you, whoops, to please open up a Jupyter notebook, and we're going to get started with Scipy. Make sure that the file that you want for today is in the same notebook as or same folder as your notebook. So mine is currently not in here. So what I'm going to do is I'm going to go to B courses. You get to see the teacher's point of view now. Yeah, okay. Let's see, Python decal. And then we'll go to, let's see, can I read this? Files. Which one is files? I think that one's files. Cool. Okay, and then I'm going to scroll down to, I have really bad eyesight. Okay. Lectures, slides, and demos. And then I'm going to download xy data.csv. So download. Cool. Then I'm just going to drag it into my same file, same folder. There it is. This is not the name that I want though. You can tell I've downloaded it a few times, so I'm just going to rename it xdata.csv. Okay, give me a thumbs up once you are ready to go with your downloaded file. Cool. Does anyone have any questions on how to do this? Great. Okay, let's get crack-a-lackin'. So, Scipy, it's kind of weird. I'm going to bring back the slides again just one more time before we get started, because I just want to give you a quick preview for what we are doing. Okay, there we go. Okay, so curve fitting is this, as I mentioned earlier. It's bizarre the first time you learn it, because you're like, why do I need to fit lines to data? Like, the data's there, I can look at it, I get the pattern, like, what's the point? It's a great question. This is because these are simple data, and the whole point of fitting a line to data is to be able to predict the future. That's basically the whole job of science. We basically want to know, under a certain set of conditions, how will this outcome turn out? So if I have a stick, and I know that there's gravity. I am going to drop this. If I drop the stick, it's going to fall. That's because we measured it, we tested it, we have theories about it in science. But things are much more difficult than just dropping sticks on the ground. There's a lot of patterns. So this could be any type of data you want. We're not really going to think about certain problems today, but maybe you're trying to figure out like the rotation of stars in the galaxy. This is actually how dark matter was discovered. Well, part of it. It was a really big piece of the evidence. So basically, Vera Rubin and others went out and they measured the velocities of different speeds of stars from the very center of our galaxy out to the very, very edges. And they're like, hey, it should like decrease as it goes out. But they found that it stays relatively constant. How did they do that? They found data and they fit a line to it, figuring out that exact relationship. And then you can figure out basically how much dark matter is in the universe by using fits. And this goes into way more like machine learning. They're just everywhere in science. We basically want to take data and we want to figure out the relationship. So that's what we're doing today. But it is weird, the whole idea of fitting data. But yeah, so that's what we're doing. Cool. All right. Let's go back to my notebook. Cool. So the first thing we're going to do, let me get my notes back up. All right, so we got a plethora of functions to import today. So the first thing I'm going to do is I'm going to import NumPy as NP. I'm going to import matplotlib.pyplot as PLT. And then I am going to import pandas as PD. And then I am going to import a very long statement. So we're going to say from scipy.optimize import curve fit. This is going to be the moneymaker today. This is the guy we're going to be talking about, curve fit. Probably one of the best functions in SciPy. I mean, arguable, but it's the one we're going to be talking about today. So those are my import statements. I really recommend anytime you importing packages. Anytime you're starting a new project, a new homework, whatever, always put all of your statements at the very top. Helps you stay more organized, helps you figure out what you're doing. So highly recommend. Okay, are we good? Hands up if we need more time to copy. Okay, I'll give you another second. All right, so I'll just leave that there. So now we're going to use what we did in warm-up, and we're going to import a file. So I'm going to make a data frame. See, concepts build upon each other. You know, we're coming back to pandas. So I'm going to equals and then pd dot read CSV, and then I'm going to import xy data dot CSV. Perfect. Okay. All right, and then I'm going to run it. Whoop, sorry, didn't even run my import statements. Okay, there we go. So now I have just imported this data called data.csv. Now what the first thing I'm going to do, as I also said during warm-up, is I care about the shape. So I'm going to print print df.shape. Shape. There we go. Okay, cool. So can someone tell me what this means? What does 61 mean here? What's 2? Oh, you guys are so smart. I don't need to be here. Okay, so the pandas, I highly recommend anytime you're importing data or you're messing around with data and tables, highly recommend pandas. You can use NumPy and even AstroPy lets you do tables, but I think pandas is just the cleanest. So great. Okay, so did you guys learn the function of how to list the first 5 rows? Nod or shake your head. Yes. Okay, what is it? Yes, good. df.head. Cool. So these are my first 5 rows. You can tell I have a column named X, column named Y, and then I have it indexed. So I go from these values to these corresponding Y values. Cool. All right. Now, how do I print the last 5 rows? Good, tail. Awesome. So just to clarify in your notes, so prints first 5 rows, and then df.tail prints last 5 rows. Great. Okay, let's keep going. So that's a bit more warm-up, bit more review from last time. So now what we're going to do is we're going to plot our data because we want to know what we're working with, even though I already gave you away the answer. You already know what this data looks like. Hint, it was on the slides, but now we get to see it for ourselves. So I'm going to make a new variable called x. And you'll never guess what I'm going to put in the x variable. I'm going to put in the x data. Great. Okay, going to do the same thing for y. Great. Okay, so now I want to plot this. Can someone tell me what is the function I need to use to plot my data? Hint, I already said the word. Yes, plt.plot. Great. Okay, so plt.plot, that will be our first function. Then I am going to plot x and I'm going to plot y. Let's see what happens. Cool. So we have this big scraggliness, but I don't really like this way to display data, especially it's a bunch of data points. So what I'm going to instead do is I'm going to comment this out. Let's zoom back in. And I'm instead going to call plt.scatter, x comma y. Great. Okay. Zoom out just a touch. Okay. So that's what I'm going to call. Now, let's see what it gives me. Cool. So now I get all of these data points, and that's much more helpful because our job is to fit a line. So we don't want just all these dots connected. All right. So now what we're going to do is I am actually going to give it this fun little marker. So I'm going to put inside of quotation marks, I'm going to do B plus. And then we'll see what that gives us. Oop. Is it not like b plus? Oh, what's the error? S must be a scalar. Okay, whatever. Maybe I don't exactly. Oh wait, maybe it's still plot. Haha, okay, never mind. Ignore this. We get to keep plot. Okay, so we're gonna do plt.pot b plus, which stands for a blue marker with a plus sign. So hence all of these beautiful b plus marks now. I don't know, I just think it looks cool. You'll find that with a lot of plotting. You'll just make it look as cool as you can. Okay, so then we're gonna give it a label. I'm gonna give it a very cool label called data. Great. All right, so now I'm gonna give it a title. So we'll just call it something like data to fit. Cool, because you always want a title, an x-axis, a y-axis, and a legend anytime you plot. If you join a research group later on and you go to your advisor and you're like, hey, look at this cool thing I did. And they're like, yeah, but what does it mean? Because you don't have an axis label, you don't have a legend, it's just a bunch of colors on a piece of paper or on your computer. So I've gotten yelled at many times for not having any of that. So avoid getting yelled at and put a title and your axis labels. Cool. So axis label for X, we will do X values, and then we'll do the same thing for Y values. Cool. All right. And then I want a legend because I want this label to show up. So legend, I'll call PLT. You'll never guess legend. Great. And then to top it all off, I call PLT.show. This basically just like combines everything into a nice little package and then tells Matplotlib, okay, you can stop. Nothing else is going to be added to this plot. This isn't super relevant for this class, but if you go on to like wanting to save your figures and like upload them to like research papers, this becomes really important. But so we just keep it in there for just bookkeeping reasons. Okay, so let's show our plot. Great. Okay, so zooming out. We have a title, we have a legend, we have all the data, we have an X or Y axis and an X axis label. Okay, hands up if you still need to copy or if we're good to go. Good to go. Perfect. All right, so let's keep moving. Still more review, but that's okay. All right, so now we'll do the next thing. So we are going to, actually, with the people next to you, I want you to talk about what is the shape of our data? And then I want you to say, what function would you write for the data? Okay, so turn to the person next to you, discuss those two questions, and then we'll come back. Hello.
I would guess you want to done the shape. Oh, right. Like, let's say,
Let's come back together. So, someone tell me, if I go back up to this guy, but you also have it on your computers, what shape of data does this look like? Yeah.
Here,
Perfect. Yeah. So, what does linear mean?
like a one to one, you know.
Exactly. So linear, as you go on in physics, it's basically the simplest relationship that you can have out there. Mostly when you like are solving physics problems, you're like probably asked to like, oh, get into like the first order approximation, and that's usually linear. Polynomial would be the next step, but this is literally just a straight line, one-to-one proportionality. Of course, there could be constants, but I'm not going to worry about that right now. So great. Okay. So if this is linear, what kind of function would I fit to this plot? Use this all the time in high school. Yeah.
Why is X supposed to be?
Perfect. Okay, so let's try it out because that is our linear equation. So, we will do, let's go back in, zoom in. All right. Great. So this looks linear. And then we will fit y equals mx plus b, where In case for those who don't know, m is your slope, and then b is your y-intercept. Okay, where it is the line that crosses your y-axis. Okay, so how are we going to do this? Great question. The first thing we're going to do is we're going to write a function. So, how do I start functions in Python? Great, def. Then I'm going to give it a name. I'll call it linear fit. And then I'm going to give it my arguments, which will be x, m, and b. Because those are all the things that can change in my equation. So whenever we're writing a scipy function, you basically want to give it all of the parameters that could possibly change along with where your data is entering. Right now we only have x. We don't have like, you like have a three-dimensional thing, it'd be like x, y, and z. But right now we only care about x. The only data we're feeding it. The two parameters I want to get out are m and b. This is just the format of scipy, so it'll make more sense as we go on. Great. Okay, so this is y equals mx plus b. And then I'm going to return m times x times x plus b. Perfect. So if we want to be nicer about it, we could do this. Okay, cool. So that is my function. Great. Now, the next thing we're going to do is we are going to call a really weird thing. So I'm just going to write it out, and then I'll explain what it is. So I'm going to write popped. You might be like, what does that mean? And then I'm going to write pcov. And just keep going. Okay, so equals curve fit. And then curve fit takes in multiple arguments. So the first argument we are going to feed it is basically our fit or our function. So that'll be linear fit. And then I'm going to feed it the variable that I'm giving it, which is x, and then the variable that I want out. So this is, if you've heard of the terms, this is my independent variable, and this is my dependent variable. So y depends on x. Okay, great. So that's what I'm doing. All right, so now I'll explain. I'll write it out as I explain just so you have it. So x comma y equals the columns of our data. And then you have these funky words up here, but I'll get to those in a second. So, and then linear fit, that was the fit we are guessing by looking at our data. And then we have curve fit, which is the scipy function that we are interested in. And then we have popped. So this stands for your optimal parameters. So what scipy does behind the scenes, it's a little bit like magic. You don't really get to see what happens unless you dig into the source code. But it essentially tries to find the minimum distance between your line and the data points. So that's what it's doing behind the scenes. It's actually kind of complicated. We're not going to get into the details here, but you're welcome to take like data 8 if you want to know more. Or you're welcome to Google it, but that's what it does. So it's looking for your optimal parameters. And then it gives you something called pcov, which stands for your covariance matrix, but that's just a fancy word for saying the error on the fit. So basically, how well does my guess, or how well does this y equal m, oh, I got rid of it, but the y equals mx plus b match the data that I am feeding into scipy. So scipy basically does all of this work for you, which is super awesome. So yeah, okay. Do we still need to copy it? Hands up. All good? Great. So let's keep going. Gonna run that. Now, the next thing we're going to do is now I want my optimal parameters. So get optimal parameters. So I'm going to call m fit, and then I'm going to call b fit, and then I'm going to call popped. So this is, does anyone remember what a tuple is? Shake your head, yeah, shake your head, no. Oh yeah, I'll remind you. So remember we just recalling way back to like a month ago when we learned about lists and dictionaries and more with arrays. Lists are awesome because you can like index them, you can mix and match, all that cool stuff. Tuples, on the other hand, are like lists, but you can't index them, you can't change them, etc. They're kind of boring, but they are nice because you can extract data like this. So we can basically hide two variables at the same time inside of one variable. So it's kind of like a magic trick again. If you like did shape and all that stuff, you would notice that, but that's what we're doing. Cool. So now I want to print my line of best fit. So I'm going to call print and then line of best fit. So y equals, so I'm going to put a little F right here because I'm going to do fancy formatting. So then I'm going to call curly brackets. I'm going to do curly brackets M fit because that's the fit for my slope. Then I'm going to do colon dot to F. You're like, what does that mean? So basically we're giving it two significant figures. That's what that does. And then I'm going to do plus B fit and then colon dot to F again. Cool. And then this should have an X right here. All right, so this is going to, I'll zoom in again. Ugh, can't fit this all on one screen, sorry. Okay, but this is the important stuff. So this is what I'm calling. Then I'm going to run it, and I get these values. So my slope is about, for every x, I get about 2.5 y, set off by a constant of about 45 values. Of course, this isn't real data, we're just playing around, but that's our fit. All right, so let's keep going. So now we have this line of best fit. So now we want to actually attach it to our data. So I'm going to replot everything. So you're gonna be upset, but I'm just gonna go back here and copy because I'm lazy. So we'll go back up here. We're gonna copy this. So copy that. Then I'm gonna scroll back down, and then I'm gonna drop it right here. But now I'm going to add a new line. So in here, so this is, we'll call this data. Now I'm going to plot my my fit. So plt dot plot, and I want it to be a line. So I'm feeding it x, and then now I want to tell it explicitly what I want y to be. So no longer am I working with the data points. Now I'm actually using a real line. So I'm going to do m fit, then I'm going to do times x, because remember, y is offset by however much the slope is, plus the constant, otherwise it would be in the wrong location. And then I'm going to set the color equal to red. Cool. And then just for consistency, because you always should have a legend, and I'm going to give it a label, and I will call this linear fit. Linear fit. Cool. Okay. We good? Hands up if you still need time. Okay, give you a second. Yeah, do you want this? Okay. Great. So you'll see if you run it yourself, a nice little pretty red line will show up. That's exactly what I had in the slides earlier. That is essentially the bones of Scipy. That's essentially what you repeat again and again and again for whatever procedure you want to go through. Scipy is pretty resilient. You can pretty much throw a lot at it. I'm not going to show you everything Scipy can do today because then I'd be up here for like 6 hours and I'm not getting paid to do that. I'm not getting paid at all. So you're welcome to come to office hours, but it's also in the homework. So have fun with the homework. I think it's fun. But Google it. Scipy can offer a lot. Okay, cool. So that is, let's plot it. Yay, there's our line. Look at how pretty it is. Cool. So yeah. Okay, so now we can also plot this in a slightly different way. So you might see the documentation tell you something different. So I'm just going to copy this again. So copy it again. Scroll down here. You can also change this line. So this should be your fit. You can change this guy right here to be kind of weird, but I'll just show you. So if you erase this, we'll instead write linear fit, and then we'll do X, and then popped. And then I'm going to run it. I'll give you a second if you want to copy it. And then I'm going to run it. And look, it does the same thing. If you ask me, what does this star mean? I have no idea. I just can't remember, but you're welcome to look it up. So that's just how you do it. That's just another way of writing it. So yeah, okay. All right. Now, let's move on to talk about some errors. This is also very, very, very important in science. You might hear like, oh, we detected up to like 5 sigmas, and you're like, what the hell is a sigma? It's standard deviation. Maybe you've heard of that, maybe you haven't, but we really care about how much error is on our measurement. Because if I go out and I try to like measure the surface of the Earth by like guessing, that would have a huge amount of error. But rather, if I went through like a systematic process of like measuring the angle of the sun relative to the shadows, that would be much less error. So we really care about the boundaries of where our data lie, because there's always error. I build instruments, so we really care about how well can we measure that one specific point. Very important. So we're going to talk about it. Highly recommend including it in your final projects. Okay, so we're going to call this P error, which stands for error on your parameters. And then I'm going to give you a weird equation. So I'm going to call NP dot square root, and then square root, and then NP dot diagonal PCOV, because this is a covariance matrix. I'm not going to go into the details of it, but essentially you have this matrix right here, and it's basically like your error, like you have like, I don't know, we'll call this A, B, C, D, and it's an influence of like how your different parameters influence on each other. That's above the pay grade of this class. That's more of a data science thing, but that's just what we're doing here. So this is just the formula. Okay, then I'm going to call M error, and then I'm going to call B error, and then I'm going to call P error. And we're going to run that. Cool. So now what I want to do is I want to see how much error is on my values. So I'm going to go print, and then on my slope, I want to know how much error is there. So M fit. You'll see this is the same thing I did earlier, and then plus, minus, and then M error, and then we'll do 2 more significant figures. Cool. So I'll run that. Cool. So I know pretty well up to about, 0.1, so not horrible. Again, there was a big spread in the data, so that makes sense. Great. Okay, so now we'll do the same thing, but for the y-intercept. So we'll say intercept, and then we'll do bfit, and then berr. Cool. Okay, so that's how well I know the intercept. It's still a lot of wiggle room on there. Maybe a different model could match it better, but not horrible. So this explicitly is your line of best fit with errors, like error bars. Great. So I didn't give you any error on the data. If I had done that, you could have done this a little bit differently, but we're not going to talk about that for today. So great. All right. Now we're going to talk about something called reduced chi-squared. Raise your hand if you know what this is. Okay, cool. Once again, a little bit above the pay grade of this class. Not everyone will need to use this for their final project, but essentially, sorry, I should have written it out. Reduced chi-squared is essentially telling you, it's how like statisticians were like, okay, what is a single number we can give to this fit, and then we can look at it and determine how good it is. That's it in non-jargony language. Of course, there's a bunch of math and formulas and stuff behind it. Take a statistics class or data 8, but it's basically a one number that tells you how good it is. So let's write it out for once, and then you can just copy it for the rest on your homeworks. So we're going to introduce a term called residuals. That'll be y minus linear fit x, linear fit x, and then we'll give it our parameters. So remember, we defined linear fit earlier to look like linear fit, and then it was xmb. So those are the variables, those are the things that can change. So then I'm basically saying, okay, for all of my data points, how far off was my line? Scipy did this for you behind the scenes, but now I explicitly want to know how far off is my point from that line. So just to scroll up, just to make it a little more clear, I have this line. This guy, he's super happy with this fit. He's like, oh yeah, you got it super correct. I'm super happy here. This is definitely my home on this red line. And then you have like this guy, and he's like, whoa, he's like, I'm really far away. And so basically chi-squared averages all of those different changes and then tells you, okay, like overall, how good of a job did you do? Okay, so scroll back down. So chi2 equals np dot sum, and then residuals squared. Once again, just ignore the math. Just copy it. I know it sucks. Okay, len x minus len popped. Okay. And then one last thing, chi squared equals chi2 divided by degrees of freedom. Not going to get into what all that means. You can talk to me after if you're really curious. Okay, so now I'm curious about what this number is. So I'm going to print reduced chi squared, squared. And then I am going to put chi. I don't want to write it, so I'm just going to copy it. Oop. Chi squared to two significant figures, as always. Y2, I don't know, it seems right. Okay, so now we're going to run this, see what we get. Cool. Okay, 408.3. So that's not too great. I'll tell you why. So, a value closer to 1 is a better fit. So the closer you are to 1, the better. But you know, like, we're not at like, I've seen, like, when I took like 5PL or 5CL and they asked us to compute it, I got like 60 million one time. So, you know, we're definitely way better than that. So it's approximately okay. It's not terrible, you know. Maybe there's something better, but also there's a big spread on the data. So maybe we just need to like tell the person who took the data, like, take better data. So it's not always your fault. Okay, so with that, we have 10 minutes, so I'm going to leave you with this question for now. I want you to turn this lecture into a function called plot fit. So take that as you may. We'll come back together, and then I want you to try that. So yeah. Yes.
Go back.
Yes. See where is it? Okay. Great. So yeah, turn this entire lecture into a thing called plot fit. Give it arguments, because you know I want to be able to see basically the data in the line. So give it arguments like x, y, m, and b, and then you want to or just x, y, and then you basically want it to plot whatever you think is the best fit. So you could like have it be linear. Maybe you could make arguments so there could be something for polynomials. Just play around with it. But a lot of coding is putting things into nice little packages and reusing them over and over and over again. So it's just good practice. So yeah, just take a few minutes. Okay, so let's come back together. Maybe you finished, maybe you didn't. That's okay. So this is what I did. I know it's kind of a weird question what I was asking you to do, but essentially I defined a function called plot fit. This is my x data, this is my y data, and then I just plopped all the SciPy stuff in here, and then I asked it to return the slope and the intercept with a plot. And then what I got was, if we scroll down, I have the plot, and then it tells me the slope and the intercept. Cool. Okay. I'll leave you the last 5 minutes to do the engagement. I'll be also here on Wednesday, so we'll do some more like practical examples. But yeah, are there any questions about SciPy? Great. Okay.
You scroll up there.
Yeah.